I'm Pam Hoffman, Everyday Spacer.
I'm Jeff Miller, Semi Computer and IT Solutions.
At Everyday Spacer, we show regular folks how to personally and directly participate in space exploration, science, and astronomy. We're here on Friday nights at 9 p.m. Pacific Time, 12 midnight Eastern Time, and 4 a.m. on Saturday in London. We're broadcasting live from Thousand Oaks, California. Thank you so much for being here. I see we already have comments. Thanks so much for being here, folks.
Hi, Janie.
Happy Friday to you, too.
Yep. Hi, Roger.
Hi, Roger. Welcome. You're up.
Yep. So, cybersecurity news. Nothing. Okay, hang on. Apparently, they're having their own conversation.
Oh yes, Thursday. We'll see you both Thursday too.
Yep.
Yay! Can't wait.
So, not much is happening cybersecurity wise, except that Tuesday was what we call Patch Tuesday. It's the second Tuesday of every month is when Microsoft pushes out its major updates, and so if you haven't done so already, you should download updates and reboot your computer, because most of the updates that they give are fixing security flaws.
Yeah, I just saw mine today, so yeah. I think they'll roll it out. With so many people, they have.
Well, they do a random time. It begins Tuesday, but then they randomly roll stuff out.
Don't forget this one too.
And we scheduled another Zoom webinar for you on October 1st, noon October 1st Pacific time. To get on the list, just send an email to jeff@semit.com.
I need to make one of those for you too.
Yes.
Or I can send. I'll show mine because you can actually send it either place. Pam@everydayspacer.com works as well.
Yeah, she can forward. Mm-hmm. But jeff@semit.com.
Yes, we should make one.
Yeah,
definitely. Did we get more?
Yes.
Comments? I think I saw you.
Oh, hey, Roger, you're talking to us now.
Hi, Roger.
Hi, Scott.
Hey, Scott. Welcome. We're so glad you're here.
At least Scott talks to us. Okay.
They can talk to each other too. It's okay.
So tonight, we're going to be talking about the Vera Rubin Observatory. We'll be back in 8.3 seconds. There's a link to that book in the description. If you want a signed copy of the book, write Pam@everydayspacer.com for details. From Wikipedia, it says the Rubin Observatory houses the Simonyi, Simonyi.
That's a family name.
Okay.
I found out in my research.
Okay. Survey Telescope, a wide field reflecting telescope with an 8.4 meter primary mirror. The telescope uses a variant of 3-mirror anastigmat, which allows the telescope to deliver sharp images over a 3.5 degree diameter field of view. Images are recorded on a 3.2 gigapixel charge coupled device, CCD, imaging camera, the largest camera yet constructed. And
let's do this first. Yep. Hey, Ron, welcome. All right, what time is it in Vietnam? I don't even know.
Yep. So what does that all mean, Pam?
We'll see shortly. I was thinking that maybe we should call it the telescope of many names. You'll hear dark matter telescope, large aperture synoptic survey telescope, Vera Rubin, Simonyi Survey Telescope, this is also from Wikipedia, the LSST, which is that large aperture synoptic survey telescope. Acronym was repurposed to refer to the survey that the observatory will perform as the Legacy Survey of Space and Time, with the camera as the LSST camera. Seriously, in the first 5 minutes of doing this research, I heard about 5 different names for this telescope. And I guess that happens sometimes, because I was looking at something else and I'm like, oh, they've renamed that one too. I am glad that they settled on the Vera Rubin Observatory, though. So I'm going to I'm going to dive right in. You want to share the screen, Jeff?
Sure.
So, as many things do, we start with a little research and happen to use Google this time, Vera Rubin Telescope, and you'll get all kinds of different things. I think this has got such a cool and potentially iconic look to it.
It looks very science fiction-y.
Yeah, it does, doesn't it?
Or she lived in a shoe.
Yes.
Just looking at it right now.
Right? I was thinking about that earlier tonight. And you've got the kind of the main things about who was Vera Rubin, you know, on and on. You could certainly dive in. And I have some of these up here. I won't go into a lot of this. Is sort of the first view of this. I'm thinking maybe I should go into a little more technical detail at some point, because there's a lot to this I didn't learn about yet. So I would love to know more. First light was in June of this year. They give all kinds of great information about the altitude, angular resolution, collecting area, diameter, focal length. And if you like that kind of stuff, it's here. You got it. I did like this page right here, which is actually from the site rubinobservatory.org /about. I mean, just look at the sky. It's so beautiful. And that is part of the reason why they put these telescopes in this location. It's high up, it's clear, and they have less atmosphere to work through.
And you can see that a little bit farther down that way is a place where you don't want the telescope.
Could be an inversion layer even.
Yeah, it's probably above the inversion layer. Yeah.
Yeah, so that's good. That's where you want telescopes to be. Actually, you want to be in space, but
yeah,
you know, we'll settle for
above the inversion layer.
We'll settle for Chile.
That's the one thing with Mount Wilson being as close to LA. It's above the inversion layer, so you don't have that moisture in the way.
Right. So I really like this because it's got a nice, you know, general overview. What is the Rubin Observatory? They give you some letters here. NSF, National Science Foundation.
Yeah.
Department of Energy, I think. Right. DOE. Vera C. Rubin. It's jointly funded, actually, by not just the United States, but all kinds of different countries have played a role in this. But they talk about the different National Science Foundation, U.S. Department of Energy, Office of Science. Is a brand new astronomy and astrophysics facility under construction on Cerro Pachon in Chile. Now, this must have been created before it was finished.
Right.
Because I mean, here they're saying first light expected in 2025.
And we've gotten it.
Yeah, and in fact, we've had first light. And I actually thought first light was something in particular, but I guess it's a little different than I thought. I thought first light was the very first time. And I think when you build a telescope, which I've done, you use first light as though it's the very first time you've set it up as a telescope. You know, because before it is, it's a blank, it's a piece of glass, and then you grind it and so forth. But when you actually put it into the telescope and you look through it, that's what I thought of as first light. But I think it's a little different according to what they have a little bit later on. If they don't find that,
it's useful for coming up with a birth date for the telescope.
Maybe, but you'll see. I hope I find it again, because you know I have quite a few tabs up, and if I don't, let's talk about it. Help me remember.
Okay.
So it is named after the astronomer Vera C. Rubin. She, and this is interesting because I do know that there were other people that talked about dark matter even before that, but they say here she provided the first convincing evidence for the existence of dark matter, and this is the first of its kind. It is a very complicated telescope camera. Like I said, I need to delve into this a little bit more at some point and give you kind of more of a crunchy technical episode, I think.
The construction of it, or the parts of it?
What's in it?
Yeah.
I've just skimmed what's like really there. I do have some pictures and stuff, but man, I can see how you can really read into this more and more and more to really get in depth on what the heck is there. What do we have to work with for, I guess, the next 10 years, really? All right, so camera sensitivity, telescope speed, computing infrastructure. It's an amazing telescope. This is, yeah, you'll see. So this is 8.4 meters. Think about that. 8.4 meters. That is big. I think there was a picture of like where it stands in the whole world of different telescopes.
Yeah, you've got it up there somewhere if we find it.
Kind of smallish, but right now it's big. All right, so
well, because most of the bigger things are proposed telescopes, nothing that's
right.
actually been built.
Yeah, not yet, and some of them will be in space because the bigger they are, the harder it is to support them on the Earth because of the gravitational pull and everything.
Yeah, which means that they'll have to be built in sections.
Yeah, exactly. So this is the largest digital camera ever built. It will take detailed images of the southern hemisphere. Yep, there it is for 10 years. It'll cover the entire sky every few nights and create an ultra-wide, ultra-high definition time-lapse record. Over 10 years, yeah, you're definitely going to see things. The largest astronomical movie of all time. That'd be a cool thing to watch, wouldn't it? This unique movie will bring the night sky to life, yielding a treasure trove of discoveries, asteroids and comets, pulsating stars, and supernova explosions. I can't wait. It's going to be amazing. With Rubin data, we will gain a better understanding of our universe, delve into the mysteries of dark energy and dark matter. There's lots of work to do there, I think, and reveal answers to questions we have yet to imagine. Again, I didn't delve into this stuff too much, but you have some sections here about construction. Again, it's built, so this would have been before, so it might be interesting to see that timeline. The innovative technology, absolutely. Some of this stuff, well, I'll talk about that in a second, but it's like, wow. Some goals, some interesting science goals. You can really just go any of these places, explore our videos. Yep. Maybe you don't like to read, you want to watch videos instead. And then there's some related content. But I'm going to go ahead with this one because look at that picture. Really, this is so interesting. And just the sky there, too. You saw the big, bright, beautiful blue sky, and now we see a big, huge... that's got to be the Milky Way, right? And if you click on it,
something else is really close to us.
Yeah, if you click on it, it's a really big picture. Look at that. And these are not, it's not movement. This is a time lapse. You see that because they're all in the same direction, and they don't look fuzzy. They look like streaks. And that's exactly what's going on there. Yep. You are seeing these stars streaking across the sky. Yes. Now, it does get a little fuzzy at the edges. Yeah. This is not taken by the telescope. I think I saw.
Oh, yeah.
One or two.
Yeah. Janie says, wow. Yeah, that's a cool image.
Yes, wow.
And
hey, Sally, welcome. All right, so I just want to let you know that this is Everyday Spacer is now sponsored by CME Computer and IT Solutions. We are so grateful. All right. So again, you can go into depth in detail with this Wikipedia page. And as you can see here by the guiding thing here, it's quite long, but about halfway, it gets into references. So I'm probably going to go through half of this, and then I'll kind of spin through the reference part that you'll see. What they really do have a lot of references in mind for this. Yeah, again.
A lot of things to dig, a lot of ways to dig. And yes. Look at how many links are in here. Yes. You can really rabbit hole this sucker.
Oh, yeah. If you like this kind of thing, you can go deep, boy. Yeah, look at this. The Vera Rubin, formerly the Large Synoptic Survey Telescope. Names, man. I'm telling you, this has a lot of names, past names, all kinds of stuff. And here they say the main task is to conduct an astronomical survey of the southern sky every few nights to create a 10-year time-lapse record. So they must have taken this right off of the Vera Rubin page, which is good because it's absolutely, you go to the source. You get the information from the source. I think it's a great place to get information from.
It's not like they're writing a report for school. They're presenting information.
Yeah.
And they're linking back to the source too. So
yes.
There you go.
So the observatory is in El Peñon Peak of Cerro Pachon, and there's the mountain range. They actually... Oh,
you can actually see the observatory, I think, right over there.
That might be this one, but remember, there are quite a few observatories in this area because it's high enough, it's clear enough,
and it's dry enough.
It's dry enough.
Yeah.
There are a lot of great aspects that help an observatory in this particular area. Now, there is some seismic activity, which I didn't realize, magnitude 5.6 earthquake. April 30th, 2012. That's not that long ago.
Mm-hmm.
I thought, well, I never really thought about it, but you think you're going to build an important telescope there, it's going to be a little more stable, maybe. Apparently not. All right, so then they go into.
I bet you there was a lot of bad shots, observatory shots as they got all wiggly.
Yes, I bet you. Okay, yeah, so they got a little more details about where it is, what it is. One of the important things I think you want to note here is that it is an astronomical survey that's building upon a whole range of surveys for really over 100 years.
Mm-hmm.
I mean, even the Harvard survey was part of this 100 years ago. Remember the women who did that?
Mm-hmm.
So yeah, there's some really great stuff here. Great image of this. It's a rendering. This is that Simonyi Survey Telescope. Now, Vera Rubin Observatory is sometimes called VRO. That's an alternative name for it. So yeah, they describe a little bit about Vera Rubin. She's was an American astronomer who pioneered discoveries about galactic rotation rates. When she noticed that these were like, wait a minute, if you have more gravity in the center of a galaxy, shouldn't it be spinning at a different rate than at the edges of the galaxy? Because of course you can see the stars and there's not as many. So, but no, it was all kind of uniform. And we actually did an episode that we talked about. It was the type of galaxy, and I remembered something from a meeting I went to for the Reaction Research Society, and I thought, well, this is a good explanation of how this is, because there was a fluid dynamics demonstration. So yeah, if you want to see that, it's the very first of the galactic types of galaxies out there, and it's a crunchy topic too. We know you love the crunchy topics. All right, so yeah, they talk about Joint Initiative, National Space Foundation, U.S. Department of Energy, Office of Science, lots and lots and lots of organizations, not just from the United States, are part of this. Now we're going to get into some fun stuff here, because they talk about the telescope, and that's really kind of where my interest lay. It's a wide field reflecting telescope with an 8.4 meter primary mirror, very big. Uses a variant of 3-mirror anastigmat. It allows the telescope to deliver sharp images in the 3 different ways that can be problematic with telescopic optics. You'll see in a minute, because I got a whole page for that 3-mirror anastigmat. I hope I'm saying that right. So yeah, this is all too correct for those problems. And I mean, this is an enormous CCD camera, 3.2 gigapixel. I mean, you think about what's in your phone, or what's in the digital cameras we used to have, and they were like,
they're megapixels.
12 megapixels.
Oh,
this is 1,000 times 3.2.
Yep.
Yeah. You were gonna say something?
Oh, just I'm thinking now Cliff is looking at his next camera purchase.
Oh boy. Hey, I don't think he's gonna get one of these. What I found fascinating too was that this has been in the process for like 24 years. First proposed in 2001 as the LSST. Construction of the mirror with private funds in 2007. Then it became a top-ranked large ground-based project in the 2010 Astrophysics Decadal Survey. And I think that has to do with every 10 years, they'll get together at a big conference and they'll decide, well, what are the important projects we should look at for the next 10 years? And a lot of times these will be recommended to like NASA. So it's kind of a big deal. Officially began on August 1st, 2014. I mean, really, that's over 10 years ago. The funding came from National Space Foundation, Department of Energy, private funding. Again, this LSST Discovery Alliance. Operations are managed by the Association of Universities for Research in Astronomy, otherwise known as AURA. Yeah, it was $680 million. I don't know if they came in that or otherwise. They started this in April of 2015. So between the start of construction, actual construction, and first light was a little bit over 10 years.
Mm-hmm.
That's amazing. So yeah, I think if you want to look it up, there's a lot more you can look at. I do want to point out, let's see, where is it here? Here's the history part. This, like I said, this is pretty important. It's a successor to a tradition of sky surveys. And that's basically taking areas and mapping them.
Yeah.
And again, with more and more and more, modern equipment.
Mm-hmm.
So, yeah. He started as visually compiled catalogs in the 18th century. Messier catalog was one of the first ones, replaced by photographic surveys. At Harvard, that was the ones we were talking about with all the women. The National Geographic Society, Palomar Observatory, that's actually south of here. It's in Southern California. By about 2000, the first digital surveys, such as the Sloan Digital Sky Survey, SDSS, began to replace the earlier photographic plate surveys. The Sloan is a very, very big deal. That's one that a lot of people involved with astronomy recognize right off the bat. So yeah, here again, look, the Rubin Observatory evolved from the Dark Matter Telescope. As mentioned as early as 1996. This is from this decadal report. Astronomy and Astrophysics in the New Millennium was released in 2001 and recommended a large aperture synoptic survey telescope as a major initiative. And now we have it. All right, so I think this is pretty good stuff here too. It talks about, it was actually not as big, 6.5 meter optical telescope, but this one's just so interesting and complex. And yeah, I think it's grown. It's going to be a much better piece of equipment for us.
Well, I think part of it was the size of the focal point. The cameras, when they were first talking about it, weren't as big or as good, and they were much more expensive to make something really big. And so
that makes a lot of sense.
So when they got a bigger camera, they could make the mirror bigger, I think.
But I have a feeling, well, of course, over 10 years, the technology will change. But if you've got the plans and you're building, you kind of can't do too much different. Unless you account for that, unless you build for that. Oh, Naomi's here. Hi, Naomi. Welcome. Hi, Naomi. So glad you made it.
Yep.
I really thought this was interesting and important too. You'll find some 10,000 primitive objects in the Kuiper Belt, which contains a fossilized record of the formation of the solar system, and contribute to the study of the structure of the universe by observing thousands of supernovae. Yeah.
You're welcome, Naomi.
All right. And of course, yeah, nearby and large redshift, measuring the distribution of dark matter through gravitational lensing. All right. And it's going to be available. You can go look at this through the National Virtual Observatory. Let's look at that one. Conceived to allow scientists to access data from multiple astronomical observatories, including ground and space-based facilities, through a single portal. And I thought somewhere, in the public, providing access for astronomers and the public to very deep images of the changing night sky. There they are. Early development was funded by small grants with major contributions in January 2008 by software billionaires Charles and Lisa, there's the name, Simonyi, however you say it, sorry, and Bill Gates of $20 million and $10 million respectively. $7.5 million was included in the U.S. President's fiscal year 2013 National Space Foundation budget request. The DOE funded the digital camera component built by the SLAC National Accelerator Laboratory. Stanford Linear Accelerator.
Yeah. Sally says, is there any telescope doing this in the northern sky now?
Not quite like this.
Yeah, because this is really big and can take a decent picture of a really big chunk of sky.
And the other factor is, too, that you don't have any, well, maybe there's somewhere a little bit like Chile, but I don't know that there is.
Right. Since the northern hemisphere is much more populated, it's harder to find a good dark sky that's in a good position to do this.
Yeah,
So,
but that is a fabulous question, and
yeah,
definitely worth looking into a little bit. And
Yeah.
of course, we have telescopes out in space too, which is kind of even better
right.
than the Earth in various ways.
So,
in various ways.
except that you can't futz with them if they're
No.
in space, especially if they're far enough away.
Not as easily.
Yeah. I'm just trying to think of where we could put something like that that wouldn't have huge cloud cover, because there's parts of the
Yeah.
U.S. that are away from everyone, but and some in the
Weather.
Just and
weather.
There's a lot of weather, and most of the places like that in the U.S. are in national parks, which Sierra Club would have a field day if you tried to build a telescope there.
Looks like Dawn's here. Hi, Dawn. Welcome.
Hi, Dawn.
It's a National Virtual Observatory. Oh,
she is.
This one here, the National Virtual Observatory.
Yeah.
Cool.
Yep.
I don't think we've done anything on that, have we? That'd be a fun episode. National Virtual Observatory. Okay.
Yeah.
Try to keep that in mind.
Yeah.
All right. So then they go into the funding from all these other things. And you could certainly go and look at that. But I really like this too. The first photons resolved by the complete instrument were detected on 15th of April, 2025. And I think here's where it talks about first light. Appearing as rings before the instrument was adjusted to focus them as dots. Images from the first light of the full telescope and camera combination were released on 23rd June 2025. And first light, is this where I saw it? In astronomy, first light is the first practical use of a new instrument, typically a telescope, to take an astronomical image after it has been constructed. This is often not the first viewing using the telescope, because optical tests have likely been performed to adjust the components, and that is true in this case too. So it's a little bit different between like what I think amateur astronomers think of as first light is the very first time you look through your telescope, especially if you built one and it's like, you're like, I want to see how my optics are, that kind of thing. And this, which is definitely a whole different tier.
And it's a different process to adjust these mirrors than there are the mirrors of a consumer level telescope, because then you have to regrind, possibly re-silver.
I just thought it was interesting to get this concept of first light, compared to what I thought was. Yeah, we got more comments.
Just
excellent.
She said hi.
Great.
Hi, Dawn.
All right, so let's see. Anything else in here I think we want to talk about? I love this too. The first teasers were a composite image of the Trifid and the Goon Nebula, and that's what this picture is here, folks. And if you've seen these, you're like, that doesn't even look like it. So this is an amazing piece of equipment. This is over 4 nights. Early images showed over 2,000 new asteroids. Watch parties for the release were held across 6 continents as people from 28 countries had been involved. There it is, 28 countries. So it's not just the United States. They talk about this Simonyi Survey Telescope. Design is unique among large telescopes, 8-meter class primary mirrors for its wide field of view, 3.5 degrees in diameter. That's big. The moon, they talk about the moon being, and the sun about half a degree. So this is some 7 times
the size of the moon. Yeah.
7. So if you imagine 7 moons or 7 suns lined up in a row, that's the kind of field of view this instrument has. I saw. Oh. Hey, someone new?
Yep, it looks like William.
Welcome, William.
Oh, hey.
Oh, excellent. From the Garden Club.
Yep.
All right, thank you. Welcome. All right, so let's see. Where are we? I just thought this was amazing how it is going to get that much of the sky to look at. All right. Yeah, for comparison, both sun and the moon as seen from Earth are 0.5 degrees. Now, okay, so each covers an apparent area of about 0.2 square degrees. All right, so that's square.
Yeah.
All right. So now that, oh, look at this. Attendu. This is something that I was over and over again. I encountered stuff like this. What is that? What does that mean? So I did a lot of this, just like I'm doing for you now. More than 3 times the attendu of existing telescopes. The Subaru telescope with its hyper supreme camera and pan stars, and more than an order of magnitude larger than most large telescopes. And here is information about the optics. And that is this beast here we're talking about. I think I even have, I have bigified this. This is quite complex. There are mirrors, there are filters, and there's something else. Oh, they've even got it's the lenses. Instead of a mirror that reflects, it's a lens that it actually goes through. So let's talk about this some more over here. Now, I love this part too about the earliest reflecting telescopes used spherical mirrors that were easy to fabricate. But I think it was there was a lot. There's a lot here before you get to what this is, what this machine is, what this equipment is. All right, let's see if I can hone in on that.
Yeah, modern telescopes generally use parabolic.
Yes, because, okay, yeah, all right, I'll go into it because it does cover, it does set us up for why this is so important and what it does. Because, they suffer from spherical aberration, and so they've gone to, they fixed that by using a parabolic.
Yep.
Making the primary mirror parabolic removes spherical aberration on axis. And I'm sitting here going, okay, what is spherical aberration?
There you go.
So, well, that looks more like an astigmatism to me.
Well, yeah, but that's basically.
And these don't look very different to me. These
except
two different pictures of
right, yeah,
the lens.
That, but the results are very different. If you notice, they don't really come to a point.
No.
In fact, our eyes are almost, I think, have spherical lenses because the different colors converge at different points, and the retina is just kind of in the midpoint in that.
Okay, so we've got our first problem: spherical aberration with a spherical mirror. You fix it with a parabolic mirror. Okay, and then you get something called a coma, off-axis coma. Now, yeah.
Basically, if something's not coming in straight.
Yeah, and this is why I'm saying it would be a whole nother episode to really deep dive into these things, because, in a week I learned about this, but it's not enough time. It's not enough time to really understand what I'm seeing here.
Lens or mirror types? That sounds like a good episode.
Oh, yeah. All right, so such parabolic primary with either prime or Cassegrain focus was the most common optical design up through the Hale telescope in 1949. Let's see what that one is. I didn't look at this one. Oh, yeah, I did. And where is that? Palomar. That's in San Diego.
Mm-hmm.
All right. After that, telescopes mostly use the Ritchie-Chrétien spherical variant, specialized variant, of the Cassegrain telescope that has a hyperbolic primary mirror and a hyperbolic secondary mirror. Yeah, see, I really want to know what all these terms mean to really tell you what the heck we're seeing here. But let's see, let's move on, because we will get into this third aberration. So we got spherical aberration, coma, and then this astigmatism, which I think it's a little bit like we talk about with our eyes, where it doesn't come quite to a point. It doesn't. Your focus doesn't come quite to a point, and so they're trying to fix all of these things with this telescope, with this very complicated arrangement of mirrors, filters, lenses, and we're talking about this 3-mirror anastigmat to fix it,
to cancel the astigmatism.
Yes, right. By applying 3 non-spherical mirrors. The result is sharp images over a wide field of view, which is what this telescope is, at the expense of some light gathering power. Okay, so you've lost some of the light gathering power you might have because of this large tertiary mirror, which obscures part of this optical path. Okay, so I'm going to go over here again because I think we can sort of see the light coming in here, right?
Mm-hmm.
And this is the first mirror it hits, and it bounces up to this thing, which would be called a secondary.
Mm-hmm.
And as we go, okay, here it is. As we go down, it looks like we hit this first mirror again
Mm-hmm.
at a different place. So they may have actually. So I really want to do this more in depth someday. They think they. What I understand is they did one of the mirrors differently. So we've probably got one grinding type here, and then a second grinding type in here. And then we go to the tertiary mirror, which is probably right there. And now we get into this whole mess, because these are filters, and there's like 6.
Mm-hmm.
Each time, though, they have to pull out one of them because they can only use 5 when they're actually recording. All right, so you've got the light comes in here, bounces up, comes back down, bounces up, and it's probably going through there to the camera.
Mm-hmm.
Okay?
Yeah, and that structure of that tertiary mirror blocks some of the light coming in.
Yes.
It's just, the price that you
well,
pay.
this one does too.
Yeah.
See, this is the light coming in.
Yep.
You hit this one first.
Right.
But yeah.
But so it's blocked both times.
Yes.
On both paths.
Right.
Yeah.
Right. So, yeah, I really want to do another episode. Okay. So let's see. Yeah, they talk about the primary and the secondary and the tertiary. So 8.4 meters, 3.4 meters, and this last one, 5 meters, 16 feet. So this is big. The secondary mirror is the largest convex mirror in any operating telescope. It will be surpassed by the extremely large telescope's 4.2 mirror secondary, which has yet to be built, I believe.
Mm-hmm. Yes.
Now, is it started? Yeah, under construction. Under construction. Oh. That's great. All right.
Did they say where?
Well, I think if you delve into this, let's see. Yeah, so probably, again.
Against the Southern Hemisphere.
It looks like it's the same mountain ridge, maybe even. Yeah. With that kind of name. I don't know for sure.
But essentially.
Yet another episode.
Yeah. But again, not in the Northern Hemisphere.
Yeah. The second and third mirrors reduce the primary mirror's light collecting area to 35 square meters, equivalent to 6.68 meter diameter. So it's kind of, it's still pretty big.
Yeah.
Multiplying this by the field of view produces an étendue, there's that word again, of 336 square meters degrees squared. Yeah, the actual figure is reduced by vignetting. Yet another. Yeah. And it's that edge. See, the edge is kind of gone.
Right, yeah.
Oh, what does Don say?
Don says it's interesting to note that the entire surface of the primary mirror is used despite the blockage of the secondary. Yeah, on the other balances, yes.
Yes. Yeah, this is an amazing piece of equipment. All right, so we're getting kind of a little bit technical here. So let me go ahead and move on a little bit. So.
Yeah, we'll do a technical version of this later.
I think so. Oh, I want to talk about this, though, because this is pretty much the grid of the CCD camera.
Yep.
And they talk about, let's see, is it here or the other page? What was it, 112? There's 2 different kinds of things here. See the blue, and then these 3 in the corner. Let's see, guide sensors and wavefront sensors. The green ones are the wavefront sensors. The yellow is the guide sensors. And this is the 3.5 degree field of view in the blue. Mm-hmm. Where is it? I think it's another page that I read the.
Oh, there's.
Oh, no, here it is. Here it is. Yes. Life-size model of the focal plane array. The array's diameter is 64 centimeters and will provide 3.2 gigapixels per image. The image of the moon, which is the little circle there, is 30 arc minutes is present to show the scale of the field of view.
Yeah. So.
And I think it'd be really fun to get Suzanne to come on the show and talk about this, but we'll see. I do have a page I'll show you about that too. The camera focal plane is flat and 64 centimeters in diameter. The main imaging is performed by this mosaic. Here it is, 189 16 megapixel CCD detectors. That's charge coupled display. They are grouped into 5x5 grid of rafts. The central 21 rafts contains 3x3 imaging sensors, while the 4 corner rafts contain 3 each for guiding and focus control. Those are those. Remember we saw the little corner ones, and the yellow and the green there.
And they do microfocus because even that high up, the atmosphere does move, and so it'll cause some slight ripples. And by firing a laser, they can detect the movement of the laser and then basically correct for it digitally. These aren't mechanical corrections because they happen too fast, but they correct for it digitally and get a much better image that way.
So I think we've gone over, in general terms, the main object here. So image data. Oh, this was pretty amazing too. Image data processing.
Oh, yeah.
Unbelievable. The amount. Look at this, 200,000 images per year. Managing. Okay, let's start over. Allowing for maintenance, bad weather, and other contingencies, the camera is expected to take more than 200,000 images. That's 1.2 petabytes, which is way big.
Which is basically a modern data center.
Okay.
That's the scale at which a modern data center is built, plus or minus a little bit.
Managing and effectively analyzing the images is expected to be the most technically difficult part of the project. And I'm sitting there thinking, ooh, I think that's where Zooniverse should come in with crowdsourcing solutions.
Well, remember, we learned about this through a Zooniverse project. They were using these images to find active asteroids. Basically, the images were already there. And that's the neat thing about this, is that you can mine these images for so many different things.
Yeah, I don't even think this was online at that point. When they got the images from some other piece of equipment in there.
And now they're getting the Vera Rubin images.
So an estimated 250 teraflops and 100 petabytes of storage are required to keep up with the data flow. This whole thing is...
Now, one thing that I don't like is that going to be over the lifespan, or is that per year? Because 100 petabytes is a lot. I mean, like I said, data centers are, in the orders of single digits petabytes right now.
This here says it's per year.
Okay.
So maybe it's the total lifespan. Yeah, 1.28 times 10 years.
Yeah.
Could be the whole of it as petabytes. And a lot of things are built in this day and age to give you, it's going to last 90 days. And it's on, like, stuff on Mars is still running this than 13 years. And crazy stuff.
So the modern data centers right now that are nowhere near that yet, I don't think, unless they've come up with some new ones, they're built next to power plants near a river, because not only do they need all that juice to store all that, but they need the water of a river to cool it.
Yeah.
So that's what they're talking about for storing this.
Now, I thought this was really impressive too. Images are processed according to 3 different timescales: prompt, within 60 seconds, daily, and annually. So these prompt products are alerts issued within 60 seconds of observation about objects that have changed brightness or position. So astronomers will get these alerts, and then they can go figure out what's going on.
Right. So they've got a program going through comparing images over time to see if brightness or position has changed.
And they do go into the where's, like the scope is on the top of the mountain, but this data processing,
as they said, like 100 miles or 10 miles away.
It's in the nearby city, but it's like at the bottom of the mountain. Yeah, I think we're getting along here. So
yeah,
I want to get on to some other things for you, not just the Wikipedia page, because there's more. There's much more. All right, so let's see.
So let's go to it.
Yeah.
I see 3 other Wikipedia pages up there, though.
Yes. I just want to see if there's anything else here. Oh, here's that image.
There's the image of.
So all kinds, and I think some of these are built.
Oh, yeah. There's the Vera Rubin.
The Vera Rubin is right here. Now this really big one, as you see, it looks like a big donut. It's an overwhelmingly large telescope. It was canceled though.
Yeah.
So they're not going to build that one. I don't even know where you could put it on Earth. But look at this extremely large telescope. Giant Magellan telescope. Very large telescope. Magellan telescopes. Large view. And this is a pretty common image if you've been involved with astronomy for any length of time. You've seen this a couple of different times. I thought some of these were actually... Oh, Hooker telescope. There we go. This is already one. This is Mount Wilson. The 100-inch. And we've looked in the window of that one because it wasn't open. Hale telescope.
It was daytime when we were there too.
Yeah, so. It was daytime, right? Mount Palomar. I think we went up. Dawn, I think we went up to that after the eclipse in Baja California. So yeah, this is where Vera Rubin sits. So some of them are about the same. And I guess, there's a couple.
The Multiple Mirror Telescope in Arizona. I wonder if that's taking surveys.
Where do you see that one? This one?
Yeah.
Yeah, because I don't know.
They
have dates on some of them. So
right, yeah.
Maybe that's still being built. That's a long time.
Well, no, it looks like it started in 1999. Yeah. So,
see, some of them have completed 2007.
Yep.
96. I guess there's two of them.
Yep. Okay, yeah.
Yeah. Anyway, so this is kind of interesting because you can kind of compare and contrast all kinds of other things. Scientific goals. This is kind of interesting. It will look for several things, and we talked about them a little bit already. The near Earth objects, and those are actually pretty important because anything could come at us. We kind of want to know that.
So 90% of the time is allocated to looking at things that people want to look at. Yeah. And then the remaining 10% is looking at areas that aren't covered by the 90%. It's like, oh, no one's looking over here. Let's take some shots of it. And probably a lot of that is going from one region to another. Like
that makes sense.
And so they just take shots as it traverses.
Yeah, I thought we had a list of the... here we go. Particular scientific goals include studying dark energy, dark matter, weak gravitational lensing, baryon acoustic. I don't even know what that is. Baryon acoustic oscillations. Okay. Photometry, supernova, and as a function. Okay, redshift. Good. Mapping small objects in the solar system, particularly near Earth asteroids. Yep. Kuiper belt objects. Expected to increase the number of cataloged objects by a factor of 10 to 100 times. It'll search for Planet 9, which is hypothetical so far. Transient astronomical events, nova, supernova, gamma ray bursts, quasars, gravitational, and mapping the Milky Way. Cool. All right. Oh, I kind of like this too. I don't think I'll delve into it because I do want to get to more of what I have set up for you, but they have comparisons with other sky surveys, which I think is important. In fact, they probably, this is probably the same spot with 3 different surveys. And as you can see, we get better and better and better at seeing what's out there. And this is a good time to look too, because, well, I guess at some point we might not be able to at all. We saw something the other night about that, and everything's going away from each other. So maybe someday.
Wow. Okay. We're talking billions of years, so don't hold your breath.
But at some point, if there are beings to see, they might not get to.
Right.
Which is
eventually
kind of wild.
Well, because the expansion is accelerating. It's already going in the farthest areas going faster than the speed of light. The expansion is happening faster than the speed of light. So as things, expand and expand faster and faster, the amount of the universe that we see will get smaller and smaller.
Yeah, look at this mirror building.
But again,
construction.
Billions of years. Yeah.
Yeah, billions of years. Telescope Mount Assembly. This is just fascinating. the pier on which it sits is also a substantial engineering project. The main technical challenge was that the telescope must slew 3.5 degrees to the adjacent field and settle within 4 seconds. 5 seconds are allowed between exposures, but 1 second is reserved for the mirrors and instruments to be aligned, leaving 4 seconds to move the structure. It requires a very stiff pier and telescope mount with a high-speed slew and acceleration 10 degrees per second, 10 degrees per second squared, respectively. This really is mind-boggling. Now, it's conventional. It's altitude azimuth, made of steel, the hydrostatic bearings. That's got to be hydrostatic, water or oil?
I think that's water.
Again, so much technical stuff. All right. Camera. They talk about the camera. Look at all these pieces of this. It's amazing. And look, I'm about halfway down.
Oh, and there's a human to show size.
Both of them. There's one there.
Oh, I
didn't see
the human on that one.
Yep. That is the camera, folks. Whoops. This is not your cell phone camera. Commissioning camera install. Let's see. Okay. Now this might have been what they took the other pictures of. Before the final camera installation, a smaller and simpler version of the commissioning camera, or ConCam, was used to perform early telescope alignment and commissioning tasks.
So they stuffed a SLR camera in there and said, "Here, let's see what we get."
See if we could do it with this one. Data transport and redaction. Oh, right. Yeah, they're going to have to be careful how much of this can be released. They can't release these images right away. They need like 3 days between the taking of the picture and allowing them to get out, because there could be sensitive, I guess, satellites. They don't actually say satellites, right? I didn't see that.
No, they don't say it, but that's likely what's going on. Is
right.
That, they've got give the intelligence community time to say, you know what?
Hey, wait a minute.
Yeah.
You can't look at that.
Yeah, we can't see this image, or maybe they'll block a part of it.
Complete images are released 80 hours later after the satellite's orbit change. Oh, they did say satellite.
Oh, so they don't block it completely. They just, if it's a sensitive one, they just hold it for 80 hours. Oh, that's the 3 days essentially.
Mm-hmm.
So it gives them 3 days to.
It's amazing. There's so much involved. And look at the satellite constellations. These are streaks of satellites, including the trains from Starlink trains. Yes. Thank you. There it is, Starlink. They've launched 7,000 satellites with plans to expand to 12,000. And then there's the other ones, like OneWeb.
Mm-hmm.
And I guess Project Kuiper. I hadn't even heard of that one before. So, yeah. Oh, galleries. Oh, I didn't even look at these hardly. But there must be some amazing images just with this kind of aperture, with this kind of equipment, with this kind of fixing the aberrations. And what a beautiful sky. Look at that. I love to see these pictures with the observatory in its environment. Mm-hmm. Look at that. That's the camera. Wow. All right. Oh, we didn't even talk about it's chilled to sub-zero temperatures. Let's move on, because there's that one, and then there's this 3-mirror anastigmat.
Yep.
Okay. So it's going to correct for spherical aberration, coma, and astigmatism. It's again used to enable wide fields of view, which is what this equipment is going to do. All right, so let's see. This one isn't a really long one, because they talk about Newtonian. Which what do I want to say? What do I want to say here for you?
Maybe just let them know that it's here so that they can dig, so that our viewers can dig into it.
They kind of go through the process of the fixing of these things with these different Paul telescope and Paul Baker telescope, Quartz telescope. Eisenberg Pearson telescope. And here, as you can see, we're getting pretty close to what is now in the Rubin Observatory.
Mhm.
Yeah, you want to read about this. Sources, all kinds of sources. All right, I did want to go back a little bit to look at this particular spot because
it shows it where it is.
It's a very small picture though, so keep in mind where that dot is, the curve here, and what it looks like, because when I looked at the picture in big, we lost the dot, but it's right around here.
Yep.
And as you can see, I mean, with the ocean on one side and this even ocean very near the other side, you've got a pretty dark spot.
Right, and as long as you're on the non-ocean side, most of the moisture in the air is going to rain out on the ocean side.
Oh, okay. Interesting.
Because it'll go up, and as it goes up, it decreases in density and the water comes out.
So there is more to this Vera Rubin Observatory page. There's a bunch of different just ways to look at this, the ways they've used this. Yeah, sky view or orbit view. I barely touched this. Like I said, 1 week, we need more time to delve into this. About the observatory, recent news, lights, camera, cosmos. This is kind of the general stuff. Oh, here we go. Bringing the night sky to life. Oh, and as you can see, there's the image of the CCD camera. The science goals. I guess we saw this in the first one too. So cool. All right. And I think it would be really cool to get a hold of someone and have them come on the show.
Yep.
So yeah, I think I'm gonna have to request this. Now I think I have one more. Do I have one more thing here? Oh, who is Vera Rubin? Oh, Vera Rubin. So wonderful.
Yeah. We do a show on her.
I don't remember.
Well,
if we haven't,
if we haven't,
we need to.
We need to, yes.
Yeah, she made essential contributions to the study of dark matter. There were others who did kind of know something about this, but she really delved into it. And some other places I've read about how she just wanted to go off and do this little research thing that didn't really seem to be interesting to anybody and really wasn't going to bother anybody. And it just broke through this whole incredible dark matter, mass anomaly problem that we still don't know. We still don't know what's going on there. Yeah, they talk about when her and her colleague Ford studied more than 60 galaxies and found that the stars at the outer edges were moving just as fast as those towards the center. They knew for sure that something strange was going on. What they observed didn't obey the law of physics. Well, it does.
We just don't know all of them.
Yes. All right, so yeah, if they added up the mass of all the unseen matter, the galaxies should have been flying apart. But they don't. Something holds them together. All right, I think this is just wonderful stuff. It's great to have a whole big observatory named after someone like this.
And it goes to show that the whole thing of the galaxies rotating same speed out as they do in just shows, the dark matter is just basically there's something there that we can't see. That's why it's called dark, not because we know what color it is or something like that.
No.
We just can't see it.
To me, it's a misnomer. It's a mass anomaly.
Yeah.
All right. So she did begin her career in the 60s and faced a lot of barriers. But she did advocate for women. And again, she kind of just went and did this thing that nobody seemed to be interested in, partly to get away from some of the problems.
Right. And then blew up astrophysics.
Yeah, pretty much. I mean, really, this is a monumental shift in all kinds of ways. All right, and I found this right before the show. I mean, literally minutes before the show. So I have no idea what it's about.
It's not almost 19 minutes long.
Yeah, almost 19 minutes. First ever images from the Vera Rubin Telescope. Astrum, ASTRUM, is the provider. So you could look up the title. You could look up the...
Maybe throw this YouTube link in there.
Yeah, it's the last one I have. So go ahead and bring us back, and maybe we'll all get to see them coming soon.
Yep.
All right. Fingers crossed this will. Oh, good. It's a short link. Hopefully that will come to you as a clickable link.
Looks like.
In one whole piece.
Yep.
So I'm going to make a quick request, though, because we are approaching our 5th anniversary of doing episodes for this show. And I would really, really, really love, please, send me a quote for our press release. I want to do a press release on our 5-year anniversary. And really just 1 or 2 sentences encouraging others, how you felt about coming to the show, what you like about it. Anything would help to get this press release going and really just to show people that I think we have kind of a unique formula here. We didn't really plan this, but with us being live, we can talk to people and we can, people come and go and they bring more information. It's, like I say, every time it's always a better show when you're here. So let's demonstrate that to other people in the world. I'm going to go ahead and flash this again. Pam Hoffman at everydayspacer.com. Thank you so much. I would love to hear what you have to say in any case, just for our edification and improvements. We're always trying to improve. But I did want to wrap up because
before
we got a comment.
Dawn says she watched the video and it's good.
That video.
So we're gonna have to watch it now.
Yay, I can't wait. So I'm gonna wrap up by saying this is a telescope of many names and many components. I saw a lot of words that I was not even sure what they meant. I'm going to have to delve into this much more deeply and probably do an episode for you on it. It has an important job in just continuation of this sky surveys with new equipment. And who knows what else is going to happen here. We just don't know. That's how everything works. We go out there with a question in mind and we ask, and then we come up with 10,000 new questions. So, all right, go ahead, your part.
Okay, some stellar events this week, September 12th through September 19th. September 12th, Uranus and the Moon are in conjunction, and the Pleiades is 1 degree south of the Moon. September 13th, the Moon rides high. September 14th is the last quarter moon, and a new globe at night project begins in the Northern Hemisphere. Look for Cygnus. In the Southern Hemisphere, look for Grus. This runs from the 14th to the 23rd, so a couple days from now.
Yeah, I think some new people here. So Globe at Night is a project whereby regular folks can contribute in a citizen science way by going out observing, report on your phone, report on your website, online, and tell them what it is you're seeing in your spot. And it's basically the whole world can participate. Yeah,
you basically take a shot with your phone, upload it to the app, answer a couple questions, and boom, you've helped them map dark skies information.
Yeah, it's an amazing project. Naomi is coming.
Yeah.
You got it?
Yeah. Naomi.
Thank you very much.
Yeah.
Oh, thanks a lot. We really appreciate you saying that.
Yeah.
Are you here?
Yeah, and we've managed to not miss a single week.
Nope. We've changed characters sometimes, but actually I like to do a lot more of that.
Yeah.
I've been out to Dawn's house and she's been on the show, and maybe we'll have to do.
One time Cliff was here and he was on the show.
He was on the show twice.
And
once with me and then once with you.
Yeah.
I actually got a break, a Friday night break.
Yeah. Yeah. So September 16th, Jupiter and the Moon are in conjunction. Jupiter is 4.6 degrees south of the Moon, and Pollux is 2.4 degrees north of the Moon. September 19th, Venus and the Moon are in conjunction. Venus is at 0.8 degrees south of the Moon, and the occultation is visible from Africa, Europe, Western Russia, Northern Canada, Greenland, and Asia. So kind of
not here.
Path. No, yeah. Kind of, if you look at that, you can pretty much see where that path goes.
There's probably pictures out there too.
Right, yeah. Also, Venus is 0.4 degrees north of Regulus. September 19th is a Friday night show. We'll bring you another crunchy topic. Find us Fridays at 9 p.m. Pacific time on the Everyday Spacer Facebook page and the Everyday Spacer YouTube channel.
Real quick, there is another eclipse on September I can speak, but not tonight. September 21st. We'll talk about that more next week, though. I just want to make sure you know it's coming so that you can plan for that. Oh, thank you, Dawn. Thanks for a great show. Love telescopes and optics. Yep. You guys have 5 years. Thank you so much.
Yeah.
So what inspires you the most for the coming week? And I have a great request for show topics. What would you like to see during an episode? Or what do you find challenging?
Yeah. I've already got one that I'm going to be doing, not next week or the week after, but soon, based on one of your requests.
Cool. So yeah, let us know and let's see if we can go there for you.
Mm-hmm.
If you or someone you know has done something interesting involving space exploration, science, and astronomy, we'd love to share our live. Join us again next Friday, September 19th. Jeff is going to do another crunchy topic, the elliptical galaxy. He said there's only 3 kinds.
Well, there's 3 major categories.
3, okay. Because I'm like...
And, okay, spiral, elliptical, and other is essentially... So we'll probably dig into that one sometime too, because it covers a lot of stuff.
But I was sitting there thinking, like, what was the first one? Galaxy Zoo?
Yeah.
Which turned into Zooniverse, which is a big citizen science platform. Did they only have 3? I can't imagine that to be.
Well, no, they had multiples, but they've categorized some like spiral versus barred spiral. For one thing, if it's that John, you can't tell the difference.
That's true.
That
John from here.
Yeah.
Yeah, we're never going to know. And Daniel has a really great Ham Micro Expo at Cal State Channel Islands tomorrow. Lots of clubs and free. Next one. Next one.
Oh, okay. Lots of clubs and free.
Awesome,
okay.
Daniel.
Cool.
Thank you so much for that information. Boy, if I wasn't doing 2 things already, I'm going to listen to do a Read It and Eat It and listen to Janie's show. Oh, yeah. She's talking about health. And Janie, what is your topic tomorrow, your main topic? I want to hear from her. She's still here, right?
I don't know. She's been quiet since.
Oh, okay. We'll do our shout out real quick while we're waiting for... We had a lot of people, a lot of good people. Janie was here, and Roger, and Scott, and Ron Rissell. Yay! Sally Sanford was here. Naomi was here. Dawn was here.
And William was here. Met him last week or the week before. It was last week, I think. And
Daniel. Daniel came at the end.
In fact, Daniel has another one. Campus is the former, Camarillo State Mental Hospital. Yes, that's why those of us from other universities call it Cal State Looney Bin. But I think most of the kids nowadays don't even remember that it was Camarillo State. And that's why it's not the Cal State Camarillo, because they wanted to get away from Camarillo State Mental Hospital. So.
Oh, boy.
But, yeah.
And Janie says... that's the topic, right? Autumn strategies?
Yeah.
With EOS essential oil something.
Yeah.
Oh. And she says 5th anniversary celebrates wood, which represents lasting love. All right. Right on. Thank you so much, everyone, for being here. It's always a better show when you're here with us. You bring us so much great information and knowledge and esprit de corps. It's fabulous. And I think we'd be bored without you.
I want to comment on Janie's comment, but
here we go.
Not that kind of show. So let's move on.
Oh God, I'm a little scared now. All right, folks, have a great week.
Okay,
we'll see you next Friday. Good night.